In this DeBacco University video, I'm going to walk you through the steps for determining the molecular geometry when the central atom has no lone pairs, as we see in this example. So when the central atom has no lone pairs, determining the molecular geometry becomes more straightforward using the VSEPR theory because the geometry is based solely on the number of atoms bonded to the central atom. There's nothing else to take into consideration. So as we saw in the title slide, the CH4, there's 4 electron pairs. 4 of those are shared pairs. There are no lone pairs. Just to give you a visual of something that's a little different, with NH3, there are 4 electron pairs, but there are 3 shared pairs with 1 lone pair, and that's going to have a different geometry. So what's a step-by-step guide here? Well, we want to draw the Lewis structure, confirm the central atom has no lone pairs, count how many atoms are bonded to it. Then we want to count the electron groups. Each bond is either single, double, or triple, count as 1 electron group. Since there are no lone pairs, the electron geometry essentially equals the molecular geometry. Use the VSEPR geometry table and visualize the shape. Use a 3D model or wedge-dash drawings to represent the geometry. All bonded atoms are symmetrically arranged around the central atom. So in this case, the BLC3 Lewis structure, total of 9 lone pairs are present here. So again, we're seeing this pretty easy to go about it because we're not having any confounding issues with repulsion because there are no lone pairs on that central atom. With those no lone pairs, the molecule adopts the ideal geometry predicted by the VSEPR theory. There's no distortion from those lone pairs. Bond angles remain consistent, and hopefully this is kind of like the easier one to understand. If we go through an example here with methane, CH4, here we've got our central atom is carbon. There are 4 single bonds to hydrogen. The steric number is 4. The geometry is tetrahedral. The bond angles, therefore, are about 109.5. As a reminder here, these solid lines represent those bonds on the same plane. Those dark kind of triangle shape here shows that hydrogen is coming towards you. And this hydrogen here with the dashed lines means that hydrogen is essentially away from you to give you an idea of that 3-dimensional shape here.